Hello, folks. Welcome to Rational Science, the only site on the internet that does physics. What are we going to talk about today? Well, we're going to talk about something that is totally unrelated to physics. We're going to talk about special relativity. And I guess you heard about special relativity. And this is more or less what we're going to be talking about today. Here it is. Go ahead and watch it. Yeah, we're going to talk about this Twilight Zone thing that they call special relativity. You are entering the dementia of what? Special relativity. Yeah, it's a lot of dementia, isn't it? Special relativity, all these strange conclusions the mathematicians reached, okay? And so it just kind of makes you wonder about them, you know, what was going through their minds, you know, when they created all this stuff. And how is it that they came up with all this stuff? Well, we're going to find out today that one of the problems is that they never define words. Mathematicians never define words. And so they get away with murder. They, they give you words, they use words that are undefined, and they claim to have proven their theories. And that's kind of strange, because you would think that the first thing they need to do is define their terms unambiguously in order for them to convey to you what they're talking about, what their theory is, so that you will understand it. But if neither they understand it nor you, the question is, what have we learned with all these folks? And let's start here. As you know, special relativity, as you may know, some of you may not know, but special relativity deals with three specific aspects: the length contraction, time dilation, and the mass increase. And we have a problem, first of all, with the length contraction, as they call it, okay? And you'll see something like this on the internet, okay? Length contraction, and you see an equation there, right? Velocity of the object, that's the v there, over velocity of light, the little c. And as v approaches the velocity of light, that v over c squared, right? That becomes 1. 1 minus 1 is 0. And if you multiply 0 times the length of the passenger, right, the person who's traveling, the observer sees nothing, I guess. Well, but we're not concerned about the math here. We're concerned about something else. The fact that they never define what length is. In fact, what they do actually is something else. They define it as distance. And the question is whether they're talking about, distance or distance contraction, length contraction. Are they talking about distance or length? And it looks like they're talking about distance contraction because they're going to unroll the measuring tape and measure something. They call it length, but they're not really measuring the length. They're measuring the distance from one side of the object, in this case, right, from one edge to the other. So they're not measuring really the length of the object. They're measuring the distance traveled by the tip of the tape. And that's where we start already with a problem. Turns out that they're not measuring distance, because distance would be simply the separation from beginning to end. That's not what they do. What they're doing, in fact, we can see this with the muon, right? If you look at the explanation they give you for the muon, and it looks something like this. What you have is that you have distance traveled from the muon from some arbitrary point to where you're going to measure it, right? And then the muon has a long ways to go still until it reaches the Earth. In this case, we're simulating with mountains, okay? So conceptually, it's the same thing. So it doesn't matter if it's a muon decaying from a pion out there in space and coming to Earth, or whether it goes from one mountain to another. We're going to look at the conceptual part here. And we're saying that, the first part of the trip is distance traveled by this object called a muon, the little red ball there, right? And what is in front of it, that light blue arrow, double arrow or double arrowheads there, right? That represents the distance that it has yet to travel until it decays or reaches the earth, or in this case, reaches the other mountain. Okay? And so what's the problem? Well, they can explain this in one of two ways. They either explain it as a time dilation issue or as a length contraction issue. When they talk about the length contraction, what they're doing is shrinking the atmospheric, the atmosphere in that region. They're saying the atmosphere shrinks, and that's how they prove length contraction. And one of the questions there is whether the distance between the two mountains has shrunk. Okay? Do mountains come closer together because a muon travels somewhere between, somewhere in outer space to Earth? Hopefully not, and then that's one issue. But then they also mix it up with the, what I call distance contraction, or with time dilation. They also analyze this in terms of time. And again, it's all irrational, because what they're saying essentially is they can decrease distance, atmospheric distance, or the distance between mountains, simply because a muon travels somewhere between them. Okay? And again, we're concerned more right now not about the actual debate on that issue. We're concerned here about the definitions. Okay? So give me a second here. Let me remove this one. Okay, and so we should really call this distance traveled contraction, okay? Because they're talking about segmented, in other words, locations where the muon was all along, from one place to another. And they're going to talk a little bit about the fact that the muon squashed in the direction of travel. They're also going to talk about the fact that the distance between mountains and between, or the atmospheric environment there shrunk. Okay? So they have all these explanations. They don't all agree, so the jury is still out on what they really mean by length contraction. Okay? But the point here is that what they're talking about really is distance traveled, either by the end of your measuring tape or by the itinerary of the muon itself. You're talking about a movie. And every frame in the movie has a location, right? And so we're talking about distance traveled and not about separation or length contraction. Okay, we're talking about distance traveled contraction. Okay, so we have a problem there, partly because they're using the wrong language, and that's a big problem in mathematics, mathematical physics. But they don't define any of these words. They don't define distance anyway, so it wouldn't matter. They define distance in terms of length, length in terms of distance. So you have a synonym, you have a circular definition, no definition at all. And they don't define time. Here you have one example. Okay, mathematician is an individual who never defines words. Never. Doesn't have a single word, critical word, that makes or breaks his theories defined. Hasn't defined any of them. They don't define energy. They don't define mass. They got like 7 definitions for mass. They use them all simultaneously. Distance traveled, whatever, it doesn't matter, because they define it in terms of length. You look up length and it's defined in terms of distance. And above all, time. They don't define time. So here you have 2 pillars of special relativity. Time dilation, right? And the speed of light, which is based on distance traveled, right? And they haven't defined distance traveled, or length, or they have, synonyms there, meaning they don't have a definition, and they haven't defined time. And he doesn't define time. He measures time. He's going to measure something he doesn't understand because he hasn't defined it, and he can't make sense of the word time. And that's what we're going to look at today, the fact that, these words remain undefined, even to this day we've known about time, for 2,500 years at least. The Greeks talked about time. Aristotle talked about time. So you can say at least 2,500 years we've had the word time, or the notion of time. And here we are, 2,500 years later, no one has been able to define the word time. So difficult to define time. Okay, that's the problem. And here's the NIST, National Institute of Standards, right? And this is what the head honcho over there says. Einstein is reported to have once said that time is what a clock measures. Some say that what we experience as time is really our experience of the phenomenon of entropy, the second law of thermodynamics. Here at NIST, right, National Institute of Standards, right, we don't worry about any of these, philosophical notions of time. They think defining a word is philosophy, ontology, word salad. I don't know what they want to call it. They think it's petty stuff. Don't define that. Well, we don't care. What they do is they measure. For us, time is the interval between two events. So they did attempt to define the word time. And they said it's the interval between two events. The problem with that is interval is defined as a period of time. So again, we have these circular definitions. These people don't pay attention to definitions. They don't realize they don't have a definition. They think they defined it. And what they're doing is just going around in circles with definitions. And it says for the most precise measurement, well, that's what they do. They measure, right? Of the second, we took the resonant frequencies of atoms. So they're going to measure. They're not going to define. They're just going to measure. And, a mathematical physicist might say, well, we don't do definition. It doesn't concern us. So why did Newton and all these people try to define time? Couldn't. And then they said, well, let's just leave it at that. And here we are 2,500 years later after the Greeks attempted it, and we have no definition of time. In fact, Aristotle defined it as the number of motion, whatever that is. Meaning, it was a mathematical calculation. That's what time is, something related to math in his mind. And, so here we have these gurus, a couple of the gurus throughout history of mathematical physics, and they tried to define time, but failed miserably. Here's first of all, we have the fact that no one ever defined time, distance or length. Mathematical physicists measure length and distance. Math is in math, length is equal to distance. There's synonyms, right? If you look them up, you'll find that length is defined in terms of distance in terms of length. And what a mathematician does, he unrolls the end of the measuring tape to measure either. Okay, or counts tiles, like you see there on the upper right hand corner there. He's like a mason laying tiles. He counts them. Okay, in math, distance equal to distance traveled, actually. Right? That's what it is. The distance of physics is separation between two objects. Distance traveled is a single object that is moving from a starting point, and you're not going to measure the object. You don't care about the qualitative stuff. What you're going to do is you're going to be either counting tiles or stretching the end of your measuring tape, or even worse, you're going to time it. You're going to say, well, how much time did it take? And of course, you establish some pre-establish some units and for distance, and you just add them up in terms of time, how many seconds they took or minutes or whatever. There is a difference. Distance traveled is segmented because it's made out of locations, right? And many tiles, many units, etc., whatever. And distance, on the other hand, the distance of physics is made of a single piece. It's separation between two objects. So you can think of it as made of a single piece, whereas the one in math is made of, segments, little pieces. Okay, so here we have a couple of these gurus. One of them is St. Augustine. He came around and says, if no one asks me what is time, right, I know what it is. If I wish to explain it to him who asks, I do not know. So again, he could not define it. But he wrote a whole book about time and God being the God of time or outside of time. And what was he talking about? He had no clue. He said he could not define it. Newton, in his Principia, the Scholium, he says, I do not define time as being well known to all. Yeah, why define it, Newt? I mean, if everybody knows what it is, you don't have to define it. What did Einie say? Well, he said, it's what a clock measures. Well, what is galloping? What would he answer? Well, it's what a horse does, I guess, right? But a horse does a lot of stuff. He poops, he eats, he has sex, reproduces, sleeps, moves, right? So which one is galloping? So you can't say what a clock measures. You can use a clock as a paperweight. You can throw it out the window and break it. There's many things you can use a clock for. And the question is, what are you measuring? And one possibility is the Heisenberg uncertainty principle. Goes more or less like this. Okay, here you'll see it. Okay, it says there's two versions of it. One is the momentum and position version, which is if we know everything about where a particle is located, the uncertainty of position is small. We know nothing about its momentum. The uncertainty of momentum is large. But the one we're interested here is the second one there. A quantum state that exists for only a short time cannot have a definite energy. So is that what time measures? Is it a measure of energy? And again, this is the problem with not defining words, one, and on the other one is just leaving it so vague, like Einstein did, what a clock measures. We don't know what it measures. Does it measure energy? Measures minutes? What is a clock measuring? And again, Heisenberg uncertainty principle, second version, maybe that's what we're measuring, energy, amount of energy, right? Well, Newton concluded if nothing moves in the universe, time would still be flowing. So he had this notion that even if the universe was standing still, frozen, right, there still would be God's clock, I guess, still running, right? Time would still be flowing. Whatever he thought about that, however he imagined that. What did Einie say? Well, he says the rate at which time passes depends on your frame of reference, meaning it's a subjective issue. Okay, because he's saying that there's no absolute time as Newton imagined it, that there's this universal clock irrespective of what anybody does, so we all measure, that is the standard against we measure our own clocks. And Einstein said, no, it's relative. It depends on where you're at, how far you are, what you see, what you don't see, depends on a lot of things. So he says time is variable. And what he held constant was the speed of light, because that's what everybody was able to prove, that speed of light travels at a constant speed. And so they said, okay, what changes is everything else. Length changes, distance changes, time changes. Everything, mass changes, right? Everything changes except the speed of light. Okay, that was a done deal. Okay, so what things do we have for time? Well, they've concluded that time passes, and that's the way everybody talks about it. Time passes, time flows. They say Newton's wrong, time doesn't flow, but then they all use that anyways. They say, well, time passes, time flows. That's the way everybody talks. Like if time were a thing that, flows around you, or passes by your eyes or whatever. And they gave direction to time, everybody puts that arrow going upwards for time. So I suppose you got to conclude that time always points north, because I see it in every single graph that I've seen. I haven't seen time in any other direction except north, right? So now space always goes east, and time always goes north. How do we say it in science? Well, time is not an object, so time does not flow. Time does not have direction. It's directionless, okay? So it's irrational to represent time with a single stick or with an arrowhead, because time does not have direction. And people say, well, the direction is forward. Well, forward's not a direction, okay? That's the problem. You can't say it goes in the forward direction. And that's very, very easy to prove. My direction is opposite to your direction. So which one is the forward direction? Which direction does time flowing in? Is it flowing in your direction or is it my direction? And so time doesn't pass because it's not an object. Time cannot be treated as a noun in physics, as a thing. Okay, it's a concept. Concepts don't move. We're done. You can't say time does this, time does that. Okay, you can't use it as a noun, as a subject of a sentence in physics. Okay, you got to say what moves, and hopefully it's not time. Okay, maybe a clock moves, but not time. Okay, here we have these people had to develop something in order to overcome the limitations of the speed of light in special relativity. Special relativity says, look, we're going to hold the speed of light constant. Okay, and I think they were right about that under the rope model. Yeah, it's very simple. Okay, how many links you have? You have frequency times wavelength there, right? And what happens when you unroll the tape, right? Untorque it. Well, you have fewer links and they're longer. And the more you torque it, you have the more links, and each one is shorter. We're done. So the speed of light, little c, 300,000 kilometers per second, right? Has to be a constant because it's mediated by a rope. We're done. No more. It's not necessary to go further than that. Okay, we're done. We can explain why the speed of light is a constant. So special relativity, really, even before that, even Maxwell, James Maxwell, he already realized that, light travels at a constant speed. They knew that already by mid 18th century or thereabouts. Okay, they were aware of that. So Einstein did not discover that. Okay? And even to this day, everybody says in special relativity that light travels at a constant speed. And that's the only agreement we have with special relativity. That is true. They don't know why, but we do. It's because it's mediated by a rope. That's why light travels at a constant speed. Okay, what happened? Nobody liked that. A lot of people said, after that, they said, well, yeah, nothing can travel faster than the speed of light because you can only increase the frequency at the expense of wavelength or vice versa. And that was a problem because you said, well, I want to travel faster than light. You got to give people hope that they will someday reach the nearest star, or that some aliens can come down here traveling faster than light, And they could not beat special relativity because special relativity says you can't travel faster than the speed of light. So this is a serious problem, right? So what they did, they created all these ideas of how to travel faster than light. And in order to do so, they had to do something very fancy. They had to create some idiotic, did I say idiotic? Yeah, I mean stupid, idiotic, irrational ideas. And they were, like negative mass, negative energy, negative time. Here's one famous fellow, and he invented negative energy. And he says, that's Stephen Hawking, right? In a particle-antiparticle pair, one will have positive energy and the other, what? Negative energy. Real particles always have positive energy. Thank God, The one with negative energy must therefore seek out its partner. A real particle close to the massive body has less energy than if it were far away. And he says, it is possible for a virtual particle with negative energy to fall into a black hole. Great. Having positive energy, it might also escape from the black hole as a real particle or antiparticle. So he played around with this negative energy, and a lot of people, bought into this stuff. He wasn't the only one, by the way, but he's a case in point, a very important case in point. He believed in negative energy. He talked about it in the course of a dissertation like if it was nothing, casually, Well, they didn't stop there. They had all kinds of energies that they invented. Here's Richard Feynman, who said, well, we don't know what energy is, let alone, what dark energy is, what potential energy is, what negative energy is. I mean, if we don't know, he says it is important to realize that in physics today we have no knowledge of what energy is. He didn't realize energy is not a what. It's not a noun for the purposes of physics. It's a noun in ordinary speech and in the religion of mathematics, but not in physics. In physics, only objects, that which has shape, can be nouns, can be the subject of a sentence. Like I like to say, you don't say the orbit of Jupiter. That's an incorrect statement in physics. You say Jupiter orbits. Orbits is what it does. So you have to phrase your language in a different way than the mathematicians talk. Okay. And you wonder how they came up with the word orbital. Well, there you have it. They're treating it as a noun. This energy level is treated as a noun. They say, well, it's an orbital because the electron orbits, I guess, I mean, who knows? But the point is that, they don't know what energy is, but they created all these kinetic energy and, potential energy. What kind of energy have they not invented? And today they're looking for dark energy. They don't know what energy is. They're looking for dark energy. I wonder if, maybe if they look for light energy, it would be a better deal, right? Okay, so anyways, here we have another concept that they invented, which is, you got negative energy, why not negative mass? And here you have, from the Wikipedia, says negative mass is a hypothetical type of exotic matter. Yeah, it's got to be quite exotic to have negative mass, whose mass is of opposite sign to the mass of normal matter. So we have minus 1 kilogram. So how much do you weigh? Do you weigh minus 75 kilograms? Is that how much you weigh? All right. Such matter would violate one or more energy conditions, no kidding, and exhibit strange property, no kidding, such as the oppositely oriented acceleration for an applied force orientation. Yeah, you're going to go in the opposite way because now you have negative mass, negative energy, negative everything. Everything's negative, right? But here's the funny part. It is used in certain speculative hypothetical technologies such as what? They call them technologies, right? Time travel to the past and future, construction of traversable artificial wormholes, which may also allow for time travel. The Alcubierre drive, right? The warp drive, right? And potentially other types of faster than light warp drives. Yeah, that's what they were concerned about. They wanted to create all these ideas of things that can go faster than light. And you might say, well, that's speculative. You have, like, for example, the tachyons. Here's the first one here. Fellow by the name of Feinberg. He came up with a word tachyon, but the faster than light notion already existed since the beginning of the 20th century. Okay, so it was been around for over 100 years. But this guy gave it the name. That's what they use it for. They talk about tachyons. This guy says he's going to prove that things can travel faster than light. Okay, and this was in 1962, was it? 67. And he's not the only one. You might say, well, it's speculative, but it's not speculative. And I'll tell you why. Because it's in the literature. And to this day, they keep publishing, peer-reviewed journals. They keep publishing about tachyons. That's more than speculative. If it's speculative, you would say, well, that's crank stuff. That's, stuff that should not be in the, in the scientific literature. It should be, among cranks and crackpots. Those people should be handling, all this stuff. But no, it's being published in all the primary sources of what we call science. Okay, here are 4 papers published in since 1982, and one of them talks about the shape of tachyons. So now tachyons have shape. Other people deny that. Here's another one. Okay, and these are the probably a little more important than the other ones because you can see, first of all, they're very close to our days, 2007, 2011, 2012. That's one issue. And the other one, look at the titles. These people are proving the existence of tachyons or fighting for them, and they're being published in official, mathematical physics stuff, literature. In other words, in their articles in the magazines that publish all their stuff from Cambridge and from Harvard and so on. So these are in the literature. So you can't say it's speculative if it's in the literature. It's being approved by peer reviewers, right? I mean, what are we talking about? What do you mean speculative? It's not speculative. They're going to be talking about it every day. And here I looked it up on Google, and you can see, tons of articles. This is just the first page, the first 2 pages, I think, of all these articles that are being published on tachyons, okay? So you can just type tachyons in a Google search, and you'll find all the stuff that all these people are publishing. So don't tell me they're speculative. And does it stay with tachyons? No. How about the wormhole? You heard about wormholes, right? In case you didn't, here it is very quickly. We had Einstein in 1935. He talked about wormholes. He created this Einstein-Rosen bridge to nowhere, a bridge without a bridge, right? It just unites two things with nothing in between. Particle problem in general theory of relativity, right? And since then, other people have started writing about it. They said, look, if Einstein said that might be an Einstein-Rosen bridge, eventually called a wormhole, maybe we can develop some math that proves their existence. Or, see, they don't usually talk about the existence. They say mathematics allows for the probability. And if it allows for the probability, it's not speculative anymore. Now it's in the literature. It's got to stay there because it's allowed for by mathematics, like negative energy, negative mass, negative time, all this stuff, all this negative stuff, right? If it's allowed, hey, then you can publish. That's the way they look at it. And here's one fellow, and Einstein. This is Einstein's paper, okay? The equation, and you can see what the wormhole looks like. This Einstein-Rosen bridge. It looks like what you see there at the top, and it says a mathematical representation of physical space by a space of two asymptotically flat sheets connected by a bridge or a Schwarzschild wormhole with a throat. This connects the two sheets and, by analogy, two separate parts of the real three-dimensional universe. Now, how's that? Is it real or not? Is it speculative, or these wormholes? No, these people are publishing stuff on all this stuff. And here, let me show you. Here's one guy who resuscitated the wormhole from Einstein 1935. This guy, his name is Kip Thorne. He won a Nobel Prize. Really, he allegedly won it because he had something to do with the gravity waves, right? But it turns out that maybe he got it for the wormhole because he came up with that idea earlier, or he developed earlier than the gravity waves. But the issue there was that if you heard of Carl Sagan, well, Carl Sagan approached him and said, look, you know a lot about all this cosmic stuff, and we're trying to make a movie. Name of the movie was Contact. And he said, we're trying to get this woman to travel faster than the speed of light. And so Kip Thorne came up and said, hey, I can do that. I'll do it through a wormhole. He came up with this idea, and he resuscitated the Einstein-Rosen bridge. And this is more or less how he, what he did. This was an interview he had. Narrator says, Contact had started something new. And Thorne says, yeah, it reintroduced to serious scientists, the notion of a wormhole as something that was really worth of thinking about. Okay, so he says, look, serious scientists should talk about wormholes. If you have a wormhole, then you can turn them into time machines, okay, for going backward in time. We thought, how could we have been so stupid? We should have realized that. That's obvious. I realized that with a single wormhole, you could have time hook up towards the future or towards the past, and that you can actually manipulate the wormhole and change how time hooked up. Narrator, suddenly time travel seemed feasible, at least in theory. And the only guy who kind of gave a word of caution was Stephen Hawking. He says, a physicist working on the possibility of travel into the past has to be careful not to be labeled a crank or accused of wasting public money on science fiction fantasy. So, was Kip Thorne doing fantasy? Was he doing science? And you might say, well, those are speculative again, No, here are the wormhole papers today, some of them. You can see there's a whole bunch of them. Again, if you type wormhole in the Google search, you'll find papers even talking about it today, right? These people actually believe that wormholes are possible, and because they're possible, that you can write about them in the scientific, so-called scientific literature, right? The mathematics literature. Here's a paper that mentions Maldacena and Susskind. I mean, you have Juan Maldacena and Leo Susskind. They're pretty big, important people, and they're all writing about wormholes. So they're all into wormhole. They believe in this stuff, and you might say, is it speculative? No, in fact, it's so speculative that you're paying for it, because a lot of tax money goes to fund all these research centers that have all these people working on this nonsense, on black holes, on dark matter, dark energy, wormholes, you name it, Big Bang. That's what they're working on. You're paying for it. A lot of them are government supported. A lot of them also are privately supported people who are deluded, who believe that these guys know what they're doing, and they're developing equations for, what did I say last time? Leprechauns and unicorns. That's what they're developing equations for. So all the work that all these people are doing for non-existence, for inexistent particles and ideas out there, like black holes and dark energy and all this stuff, it's all worthless garbage. You won't, we're not, we can wipe it all aside, throw it in the trash can. The last 40, 60, 70 years, they haven't made a single inch of progress. That's what I'm saying. Okay. And you paid for it, and you're still paying for it, just in case. Here's a wormhole article that this person wrote recently. And you can see, and she's a physicist, mathematical physicist, right? Mathematician. Says one possible solution to the general relativity field equations is a wormhole, okay, a kind of tunnel connecting 2 points in space-time. And they act as a shortcut through space-time, connecting 2 points within a single universe. Okay, and then it says a wormhole has never been observed either directly or indirectly, but relativity field equations, allow for the existence of wormholes. So as long as the equations allow for it, you are welcome to write about them and publish, right? And you'll be treated kindly by all peer reviewers, right? Exotic matter, what is it? A form of matter that has negative energy, density, and negative pressure, and is repelled rather than attracted by gravity. And what do they use it for? Exotic matter could prop up a wormhole tunnel open with its gravity repelling abilities. So if you want to keep the wormhole open, all you have to do is put some negative energy, or maybe some negative mass, or who knows what, negative time. Wormholes are a popular subject among science fiction enthusiasts and theoretical physicists alike, okay? Because they're all dreaming about being able to travel faster than the speed of light. That's one issue. But the other one is to give hope to people. And a third one you could say has to do with the fact that it gives job security to a mathematician, because he can now develop equations for a wormhole that the theory of relativity does not deny, or the possibility of it existing. So you end up paying for all this nonsense that all these mathematicians are researching, that they feed you as truth, as proven through experiments or through the equations. And this is the world we have today. Okay, so keep all that in mind. Here's good old Brian Greene, just in case. I mean, you've heard of Brian Greene. He's got a PhD in who knows what, right? And it turns out he's going to put it in his documentary about, science, what they call science. It's really, mathematics, a lot of physical interpretations that are worse than, falling into Alice in Wonderland's rabbit hole, okay? And here you'll see it, okay? Let me show you this. This is how he illustrates it. Here goes.
Now, time travel to the future is one thing, but what about time travel? Well, that might be possible too, using something predicted by Einstein's equations, known as a wormhole. If wormholes exist, they would be kind of like shortcuts through space-time. Tunnels that would link not just one place with another, but also one moment with another. preserve subway systems through time. So, let's say I wanted to go back in time and meet myself at the beginning of this program. If a wormhole connected here and there, all I need to do is step through. Hey, good to see you again. Thanks. Good to be back.
So, was that science? Did you get your science shot for the week with all that? Is that what they call science? Is that what you're spending your money on? Not only are you investing money in these people to do equations for inexistent stuff, but you're paying also indirectly for all this Hollywood stuff, which they, I mean, if it's a movie about someone traveling faster than light, no problem. These people are making documentaries, feeding it to the public as documentaries, as if this were science. And so in that sense, a lot of money is going in that direction as well, into documentaries which have nothing to do with science or physics or anything like that. It's all garbage, nonsense. And I'm being kind. I'm just calling it garbage. Sorry, I can't use worse words in my transmission, okay? How about warp drive? Here you have a fellow named Alcubierre, and he came up with a warp drive. He said, the Alcubierre warp drive is an exotic solution in general relativity. It allows for what? Superluminal travel at the cost of enormous amounts of matter with negative mass density. Yeah, they had to create negative mass, negative energy, negative all this negativity. They had to create it in order to be able to show you how you can travel faster than light. Yeah, I mean, if you weigh negative 75 kilograms, I guess you could go backwards in time as well. I mean, I don't know. But listen to Alcubierre. This is Alcubierre's testimony of what he did in the last 20 years. Essentially, since he published that paper. He says he never went back to that paper, never dealt with it again, with the Alcubierre drive, right? And that's not important. What I want you to listen is what he's been doing for the last 20 years. What kind of stuff you're paying for. He's in Mexico, right? But this is the same thing all over the world, okay? Whether you're in China, Russia, Europe, it doesn't matter. Everybody's doing the same thing as this guy. And here, listen to him, okay? Just listen to what he has to say about what he does for a living.
These days I've been working on black hole formation and also on something a little bit esoteric that we call boson stars, which is a model for a star made of a special kind of field that could mimic a black hole in many circumstances. So I've been specializing in that area, and my work is mostly numerical simulations. So for a long time I've been doing numerical simulations of black hole spacetimes, formation of black holes, collapse of stars, and also gravitational waves, production of gravitational waves. So that's my main work, and I've been working on that for the last 20 odd years.
Okay, so now you know what you're paying for. You're paying for all these guys to develop equations for nonsense such as warp drives, wormholes, tachyons, anything that can take them out of the craziness of our of our world. That's, I guess, what they're looking for. And of course, they invented negative time. Here you have a recent article that came out. It says physicists showed that photons can seem to exit a material before entering it. Okay, so yeah, I guess they arrive before they leave, kind of thing. And quantum particles are familiar with wonky familiar with wonky, seemingly nonsensical phenomena? Yeah, I guess they are. And that's what you're paying for. You're paying for what? Wonderland, Alice in Wonderland, rabbit holes, or who knows what. That's what these people are developing. And you're letting them get away with it. Okay? So, yeah, they finally came up with negative time as well, so we have all these negativity out there. And I said, I'm not going to be outdone by all these people. They're not going to beat me. And so I invented my negative stuff too. I developed a new idea that you can consider. It's called negative force, okay? It's called pull. Pull is negative push, right? You throw the ball, you would think you'd push the guy away, but because we put a negative sign in front of that push, we have pull. Okay, so I want you to give me credit for that. I was the inventor of the negative push. It's also known as pull. Okay, and here you can compare it against, one against the other. So you see what the difference is. One case you throw the ball and you push the guy away. In the other case, you throw the ball and for some reason, the guy comes towards you. Okay, so that's called the negative push. Okay, from now on, you can even use it as a synonym for pull. You don't say pull, you just say, today I had some negative push. Okay, it turns out that unfortunately, I found out that I'm not the inventor of that. Later on, I found out because they beat me to it. They also had invented that. And here you have one guy, Victor Stenger. He was from the University of Hawaii. And he says, the vacuum is capable of producing interactions between particles at effectively space-like separations. This occurs when quantum fluctuations in the vacuum cause a particle to zigzag backward and forward through space-time. No doubt the idea of motion backward in time makes a grievous assault on common sense. Yeah, no kidding, Vic. And however, to a particle physicist raised on a diet of Feynman diagrams, motion backward in time is not all that disturbing. All fundamental particle interactions work backward and as well as forward, and with rare exceptions do not distinguish between the directions of time. Okay, so yeah, he already beat me to it. He already figured out that you can have negative push. They call it negative momentum transfer. Okay, so all you have to do is, throw the ball to the catcher. You're the pitcher, and you can draw the guy towards the mound. Try it one day, okay? I'm sure you'll succeed. So is that where we stop with the negativity or irrationality of special relativity? The fact that they don't have definitions, the fact that they're trying to outrun the speed of light, which special relativity says it can't be outrun, but they say they give lip service to that when they're in their freshman or sophomore year in college. But then when they get higher up, they say, no, but we can beat the speed of light because we'll overrule it with a wormhole or with the warp drive or whatever, tachyons, right? And so, we didn't stop there. Here we have Stephen Hawking again, guru in mathematics, and he invented the what is known as the imaginary time. So we have not only negative time, we have imaginary time. It says a particle does not have just a single history as it would in classical theory. Instead, it is supposed to follow every possible path in space-time. So remember, a particle can be at all places at once, not only at two places, but at all places at the same time. And in fact, it is everywhere at once. Okay. So I hope you understood that, right? I hope you can picture that. The probability that the particle, say, passes through some particular point is found by adding up the waves associated with every possible history that passes through that point. One must add the waves of particle histories that are not in the real time that you and I experience, but take place in what is called what? Imaginary time. So now we're talking about imaginary time. That's what they're developing equations for. Imaginary time may sound like science fiction. No kidding. But it is in fact a well-defined mathematical concept. It's a mathematical concept, folks. They call it mathematical concept. Why? Because they need to do research on this nonsense that they call imaginary time. Okay. And so he says imaginary numbers are represented by a line going up and down the page with I, 2i, etc. I being, the square root of -1, irrational numbers or whatever. And one must measure time using imaginary numbers rather than real ones. This has an interesting effect on space-time. The distinction between time and space disappears completely. Yeah, and this is the issue. These people treat all these things as, the space and time as just number lines. That's why there's no distinction between them. They're not talking about dimensions. They're not talking about length, width, and height. They're not even talking about coordinates. They're talking about number lines, and they can fit as many number lines as they want because number lines don't have direction. They go 90 degrees to absolutely nothing. A number line can go in any direction. You can put numbers anywhere you want, right? And so when they're talking about dimensions or coordinates, they're really referring to number lines. And so space-time is not four-dimensional, it's four-number-lined. Okay, keep that in mind. Okay, so how do they define time after all? Let's ask some of the gurus of mathematical physics. These are well-placed people, a lot of them big names, celebrities that you've heard about sometime in your life, most of them at least. Here it is. This comes out of the same interview that they had with Kip Thorne, okay? Matt Weiser says, time is something which at a fundamental level we don't understand. Yeah, after 2,500 years, they don't understand it. Newton, of course, thought time was like a river that flowed, and Kip Thorne adds, time is the thing out there that flows, and I go with the flow. So they think it's a flow of something. They use that word flow, and you can say, well, they're being facetious. They're using figures of speech. No. Either there is something called time that flows like a river, or there ain't. It's just that simple. It's black or white. You can't say that in physics you're going to talk about the flow of time and then say, well, I was just kidding. And go to philosophers to find out what I said, what it means. No way. You got to tell me. John Wheeler, time is nature's way to keep everything from happening all at once. That's about the best one they had. And what did Carl Sagan say? It is one of those concepts that is profoundly resistant to simple definition. Simple or complicated, they never define the word time. That's the status quo, okay? They have no definition for time. But they reach all these conclusions based on this undefined term. That's what's very suspicious, right? We don't have a definition for time, but we do have a definition now that we can solidly chew on for what is a mathematical physicist. And here it is, okay? Mathematical physicist, also known as mathematician, okay? Individuals who boast of how smart they are and then base their entire repertoire of irrational theories on the undefined word time. That's what a mathematical physicist is, especially a special relativist, okay? They reach all these irrational conclusions, but they never define the word time, and that's the one they're going to use to make their case. So, we got a problem there. These people don't know what time is, but they talk a lot about time. It's one of the most important words in mathematical physics. Okay, so how do we define it in science? Not that, the word time has no place in science, by the way, okay, or in physics. We do not use the word time because in science and in physics, what we do is explain, and time is a descriptive word, can only describe. It has no power to explain anything. That's why time is not part of physics. Time is not part of science. We do not use time, okay? They might use it in technology. It's got nothing to do with science. Science, we have to explain a mechanism, and time helps us explain absolutely nothing, okay? So here it is. Let's see if I can show this here. This is, again, the NIST said, keeping time at NIST. Time is an interval. What was an interval? The same thing as time. So they had no definition. How do we define it? Well, it's a comparison of two motions. That's what it always was. For example, you take the pendulum, right? Any pendulum. This is just an example. And you take the rotation of the Earth around the sun, revolution, right? And it's called 1 year. And, you're measuring these two motions. You're comparing them. Time requires an observer, memory, okay, a recording device, okay. And here's another version of that. Here you have the clock. Let me put this up here. Okay, you have the Earth going around the sun, and you have and you measure the seconds on a clock. So if you the second hand on the clock, right? What it measures is that 1 second is equal to 30 kilometers of the Earth going around the sun. So if you have 1 second on the clock, you have 30 kilometers on the Earth. And you're comparing those two motions. That's what time is. Okay, that's what a second is. And again, time, simply comparison of two motions. And a comparison of two motions is not a physical object, by the way, because they treat time, they say gravity warps time. No, only if time is a physical object. And you can't say, well, they were just using a figure of speech, an analogy. An analogy for what? A simile of what? You can say that the canvas of, a trampoline, right, warps like a banana. That's a simile, because we all understand banana is warped, and you're saying that this canvas, this trampoline, is warped like the banana. We all understand that. But to say that number lines are warped like, time is warped like what? Like a banana? No way. Time is not warped like a banana, because that's not a simile. Time is a concept. Is love also warped like a banana? Is intelligence warped like a banana? Right? It makes no sense to talk about, concepts being warped or bent or, any of those words. Like you use a word of physics to represent a concept. No way. Not in physics. And that's part of the issue. Okay, so what can we conclude more or less about special relativity? Well, here's just a quick rundown. Special relativity conclusions are based wholly on the constant speed of light, and the variability of mass and distance and the relativity of time, specifically the relativity of time. That's where they're going to get their time dilation notion, right? The idea, theory. If there's no such thing as time, if time is a concept, then time does not exist. Only objects can be said to exist in physics. You cannot say that a concept exists in physics. If you don't like the definition of exist, object that has location, you want to have a concept that has location or concept, whatever, you define the word exists, and then we'll know what you mean by exist. Define in such a way that you can not only defend it, but that you can use it consistently. Okay? And special relativity suffers a sudden death without time. Okay? Time is not a thing, so it cannot flow or move. Time has no direction, right? Direction is a qualitative concept and has no business in math. You cannot put direction in an equation. What are you going to put for direction in an equation? You can put a number, you can put a variable, you can't put direction. Okay? And direction belongs exclusively to physics. Father Universe, what I'm going to talk about next, recognizes no such notion as time. And that's the one that's going to defeat special relativity completely. Okay? Just get rid of it completely. Time is an invention of living entities. Okay? So let's go with that. The last two there. Let's show why you can't use the word time, not only in physics, but, if you can't use it in special relativity to make your case in special relativity, it's the end of special relativity. All the measurements that they made, all the theories that came out of that, all the conclusions, down the drain, down into the trash can where they belong. The ash heap of history. Okay, so what is this? Let's start with time dilation. Okay, the equation, here it is. This is just quickly through there. We're not going to do any math here. We just want you to understand the concept for those of you who are not familiar with it. You have time of the observer, guy looking from afar usually, right? That's the way they present it. And you have a passenger. It could be on a train. It could be on a rocket. We don't care. But there's a passenger traveling close to the speed of light. So you have that velocity of the passenger right at the bottom there over the velocity of light. That's equation number one. Let's do it with some numbers real quick so you can understand how this all came about. If you're traveling at 99% of the speed of light, which is equation number two there, well, you're approaching the speed of light, which would be equation number three, right? You're almost c squared over c squared, and that's 1. 1 minus 1 is 0. Time divided by 0, guess what? Undefined, infinity, etc., right? Or the laws of physics break down at the singularity, whatever term you want to accept, okay? So the law of physics broke down because, you traveled at the speed of light. And that gave them an idea that nothing can travel at the speed of light, or, either at the speed of light or faster. That's the only one they got right, but they don't know why. Again, physically, we do it with a rope, no problem. Okay, so that's where we start. That's the equation, right? Okay, so where do we go from here? Okay, one of the things they tell you based on this equation, one of the conclusions they get is that if you're up there in outer space, time rises very slowly, whereas you're close to the if you're close to the center of the earth, time runs very fast. They said gravitational effects make time run faster. So if you were on top of Mount Everest, or even in a building, they said, like if you're at the Empire State Building and you're at the top of the building, at the bottom of the building, the guy at the bottom of the building, time is going to run very fast and time at the top is running slow. That's what they tell you, okay? And everybody just accepts and say, yeah, okay, so they proved it mathematically, et cetera, And no, it's absolute nonsense. So that's the first notion that we want to tear apart. Okay, here it is. Here's Einstein and his cesium clock, his atomic clock. And he puts it at the bottom of the Eiffel Tower and the top of the Eiffel Tower. And he says the run at the clock at the top runs fast. He says it runs. The clock runs fast. I guess I got those in reverse, maybe. I don't remember now. The one runs closer to the Earth has to be running faster, I think, because let's see. When you're out in outer space, the twin, for example, that's out there, his age, he ages very slowly, whereas the guy on Earth his age goes very fast. In other words, it goes according to the motion of the Earth around the sun. So I'm not sure if I got that right there. So I'll have to say something different there. My point here is that we don't need an atomic clock to measure the speed of time, right? One way or the other. We can do it with an hourglass. If you have an hourglass up there in outer space, it's going to go very slowly, and the one close to the Earth is going to run very fast because it's closer to the source of gravity, which is the center of the Earth. So if you have one at ground level, that clock should, this clock, here it is, okay? This one should run fast, okay, if you're in close here to the Earth than if you were out in outer space. In outer space, because gravity is less, right, this should run slower, okay? And that's essentially the opposite of what Einstein said, okay? Sometimes I get these confused, okay? But that's one issue, okay? And another issue is the famous twin paradox. You have one twin leaves the Earth, right, and the other twin stays behind. And this is more or less what they're referring to. Let me illustrate that for you here. Okay, here it is. Okay, you have one twin, and he's going to leave the Earth with his rocket. He's going to go to a black hole, turn the corner, right, and come back. Okay? And so the question is, is time the same thing on the rocket that it is on Earth? That's the issue that they're trying to answer. Is that what happens? Is the time the same or is it changes? And they say the time is different for the guy who's traveling, okay? But they reach the conclusion because of that the guy on Earth did not age. He aged a lot, whereas the guy who traveled did not age hardly at all because he's traveling close to the speed of light. And this is the way they more or less they illustrate it. Okay, here it is. The illustrations are mine, by the way, but I try to illustrate what they're trying to say as best as possible. Okay, and here it is. Okay, so we have this fellow. He's going out, and you can see the clock running fast. Okay, and the guy who's traveling, his clock is running slow, and so he ages very slowly. The guy on Earth, his clock is running very fast. He's aging, I guess, faster than the guy who travels. Okay, that's the issue. So he might be 40, 50 years older than the guy who traveled. That's essentially what they're saying. Okay, and so how do we answer this? Well, one way to defeat that, we already looked at the hourglass being on top of Mount Everest or the Eiffel Tower being slower than the guy at the bottom. That's one issue. The other one is, you can do this experiment of the traveling twin and just imagine they take a rope, okay, a long rope, and you put knots on the rope, okay? And between any two knots, you have the distance that Earth travels in 1 year, okay? So between two knots, we have the distance the Earth travels in 1 year, and you count all these knots. Let's say you went 10 years outwards, came back 10 years. So that's, 20 years, right? Hopefully, when you arrive back, you both aged the same amount of time because the same amount of time passed between both of you. You don't carry an atomic clock because they're notoriously inaccurate at different distances and at different temperatures. Here we have knots, right? That's very straightforward. You have a knot that is I think it's 940 million kilometers from the other knot. So you have all these knots, and they're all, over here. There it is. We have all these knots, and one knot's here, the other knot's here, right? Between them, you have the distance of that the Earth travels in 1 year, which is the standard for the year, which is the definition of a year. Here's the definition of a year, right? Looks more or less like that. The Earth travels around the sun, and once it goes one full revolution, that's what we call 1 year. And so that hasn't changed ever. We still have a year being measured by the rotation of the Earth around the sun. So if you want to know how old anyone is, I don't care how far he traveled. I don't care how fast he traveled. I don't care if he went to the other universe through a wormhole and came back. When he comes back, we just need to count how many times the Earth went around the sun, because that's the definition of the word year. Okay. And again, the other way you can do this is, measuring the, with knots. That's objective. Knots do not dilate. Okay. And here it is. Okay. Let me show you. Here it is. Watch it. You can see the rocket's going, and we're going to take this rope. We're going to count, how many knots we had, okay? And hopefully you got 10 going out, 10 coming back in, if you release the knot from your ship as you're flying, right? It should be straightforward. We should be able to count to 10. And I hope the mathematicians can count to 10. And so, if you do it this way, the times the Earth went around the sun has to be the same as the number of knots, which would be 10 going out, 10 coming back. That's 20 years. They both, the two twins should have aged both 20 years. Period. We're done. There shouldn't be any question about this, because this is straightforward math. And if they can't do math as simple as this, well, I don't know. Okay, but there's a more fundamental reason for why special relativity dies a sudden death. Father Universe does not recognize time. He has no idea what time is. We humans, or other living entities, we're all aware of time. Even a lion is aware of time in a very rudimentary manner. He looks at the wildebeest or the zebra, right? And he already has a notion of how fast they run, so he gets up close, the lion gets up close, looks at the zebra, and knows at what point he can start running and trying to catch that zebra, right? And so, if another lion is watching the whole scene, he's seen the lion when he was hiding, and he saw the lion when he caught the zebra. So he's got a notion of time. He's got a sense of time. He has that before and after. He's got the starting point and the ending point. So even though he can't do calculations or whatever, he's got this notion of time, this rudimentary notion of time. So to say that animals don't have time, they do have time. Even the lions, I guess, always wait for for this great cycle of the movement of many animals, right, that they're going to hunt. They know when it's the season to be jolly, because the herds come back close to where the lions are. They know that's the time of the year to go hunting. So they have a sense of, calendar, of time. They have a little sense of that. That's my take on that. But what's the issue? The issue is that Father Universe does not recognize time. So let's look at that. Time dies with Father Universe. There's no such thing as time. And here you have the Universal movie. Okay, what is that? Well, this is a movie of the universe. In one frame, in a single frame, you only have static concepts. Okay, you have only every atom in the universe, right, at a given location with respect to all others. Okay, so there's a distance between every atom in the universe at any given point in time, so that in a single frame, you have no motion whatsoever. If you want to see motion, you need to roll the movie. But it turns out that, Father Universe does not do that. He can't do that. Father Universe always looks at himself, and that's what he sees. So if God were to take his camera and take a picture of the universe, you could think of it as a three-dimensional movie. That's why I put the projection there. But what you're talking about, every atom in the universe, right? It's at a given location, at a given distance from all others. So this is Father Universe, only one frame. Father Universe does not recognize motion. He goes to sleep for another 1,000,000 years, then he wakes up, every atom is at a new location. Okay, and that 1,000,000 years is a split second. Like they say, it's God's time, so to speak. Okay, yeah, there's only a single frame. Okay, and so when we look at something like, they talk about an event in special relativity, where this event happens at a certain time, but the observers at different distances, at different locations, they don't measure the event simultaneously. So it's this notion of simultaneity that drew us into special relativity that, they emphasize. And so let's look at an example here. We have, this is the first frame in our movie. We have two observers. Okay, and there's going to be an event that happens, and it's going to be, we're going to make it a supernova. Okay, how's that for an event? So a supernova happens, and at the moment it happens, the frame in which it happens, right, is right there, 632. But neither observer has yet seen the event happen, because they're too far away. So in the frame in which it happened, they didn't see it yet. Okay, they're still trying to figure out, as far as they're concerned, they're blindsided to the event. Okay, and again, the event, you can say, takes up more than one frame, but that's not what we're talking about. We're saying the moment the explosion happened, the exact frame of the movie, if you were to take a snapshot just when it's about to burst, that's the frame that we're looking at there. Okay, so what happens next? Well, the beam travels, and still neither observer has seen the beam. Okay, so as far as they're concerned, nothing happened yet. Okay, in frame number 634 now, what we have is one observer, the one closest to the event, sees it for the first time. Okay, so he sees it, but the other guy hasn't seen it. So as far as observer number one, he sees it, and so you can say, okay, he's now aware that there's been a supernova, but the observer number two has not seen it at all. So this is what special relativity thrives on. Okay, so next frame, still the first one has already finished seeing it. It's no longer there, maybe, for all we know, right? Or maybe he's still watching it. But the important thing is that the second observer still has not seen it, even in frame 635. And finally, we have this situation where the observer finally sees it. Okay, here it is. Finally, the light reaches his eyes. Okay, so this is more or less what special relativity talks about, the fact that different observers see different things, measure different things. Now, as you can see, it hasn't changed the frame 632 in which the event happened. Okay, that is not a question of, that's the universal movie, you could say. The fact that Father Universe does not recognize movies, something happens within a single frame, or you cannot say happened. You can say if you take a snapshot of what's about to happen, that happening, in fact, you could take frame 632 and 633 also, and you can say it happened in those two frames and still no one saw it. Neither of the two observers saw what happened, okay? But actually, Father Universe only exists in a single frame. So as far as Father Universe is concerned, all the atoms in the universe at a given location, frame 632 represents the simultaneity of the occurrence of the event, which is not really an event. It's just a snapshot of a given point in the event. That's what it is. And the other guys, both observer number 1 and 2, have not seen it yet. That's the issue. Okay, but it turns out that I did this wrong, completely wrong. Why? Because I'm misrepresenting Father Universe. Let's represent him the proper way so that we can understand what's going on here, okay? Here's again, frame 631, nothing's happening. We see two observers. Okay, what happens next? Well, what happens next is there's a supernova, right? But it's in a single frame. See, we don't have all the frames of the movie because Father Universe doesn't recognize the entire movie. Father Universe does not recognize this. That's not what he sees, okay? As far as Father Universe is concerned, he's not in many frames at the same time. He doesn't have atoms in every location that we had in several frames of the movie. No, he only recognizes one frame, and that's that one. That's the only one he recognizes. So when the light is still traveling, like to the two observers, and none of them yet see it, that's all Father Universe experiences. Every atom in the universe at a given location. There is no movie as far as he's concerned. Movie is an observer-related issue, right? Idea or notion. And here the first observer sees it, the other one doesn't see it, okay? And again, what you're seeing is that, certain things happen in certain frames of the movie, and what each person measures, here he doesn't see it, and here he does see it, okay? What all these people are doing, they're measuring, and measurement has nothing to do with what is. The fact that someone measures something a little later than the other guy has nothing to do when the event actually happened. And that's where people get confused. They say, well, did the event happen at a given time or not? And it did happen in this, you could say, universal time, which is just location, okay? In that frame of the movie, it happened then, okay? That's when it happened. When people measure and what they measure, that's subjective. That depends on how much distance they have, how fast light is, etc. It depends on something totally different, but it has nothing to do with when the event happened. You can't change that. And one of the issues there is that, again, you can't go back in time because there is no frame of the movie, no atoms in that frame of the movie that you still remember in your brain. That one doesn't exist anymore. Those atoms are now somewhere else in the universe. So you cannot go back in time with a warp drive, with a wormhole, with a tachyon, writing a tachyon. You can't go back in time because there's no place to land. Okay, there is no frame of the movie called the past. Okay, it's not there. All the atoms have moved to a new location in the entire universe. And again, if God takes a picture of every atom in the universe, a 3D picture, and shows it to you, you would see just every atom in the universe at a distance from all others. And there is no other picture. He can show you the picture, but there's nothing to land there because those atoms are no longer there. And that's the problem with time travel. In fact, the universal movie destroys actually the entire language of mathematics, of mathematical physics. Why? Because here you see that these people say that mathematics is the language of physics, right? And that's only if you're looking at a movie. Then you can use the word time, you can use the word energy, and all these motion words, okay? What does Father Universe recognize? He only recognizes a single frame of the film. And all you have there is illustration. You have objects, static concepts. Okay, that's all you have in one frame of the movie. And so this notion that the mathematicians have developed that you can have all these words such as time and things that involve motion, such as energy and mass, that's us. That's us humans. We invented all these concepts. In fact, all concepts have been invented by man. And Father Universe only recognizes static concepts like object, like, distance, location, existence. That's what Father Universe is, because that's all, that only shows the atoms at a given location with respect to all others. Can we figure out what this universe is? Very easily, and I showed this the other day. You have let's do it this way. You had the two atoms bound by a rope. This is the basic system. Two atoms bound by a rope. Multiply this by a very precise number such as gazillion, and that's the entire universe. That's the entire matter of the universe. Atoms bound by ropes, all interconnected across the universe. What serves as a backdrop to that? Nothing. We use the word space or vacuum to refer to that nothingness. So we have this nothingness, which is that which has no shape, and we have the somethings, all these atoms bound by ropes all across the universe. And that's the something. We have the something and the nothing, and that's the definition of the word universe. With that, I'll see you next week.